Hello everyone, I'm Dr. Hussain Haidari, and today we're going to talk about processing and manufacturing of polymers. Throughout the course of the past 2 weeks, we've looked at a couple of different concepts in polymers. We've looked at the structuring chemistry of polymers, very basic level. We've looked at the monomer units that construct these polymer chains, and we've looked at polymerization in general, how it occurs, what the chain reaction looks like. We've looked at how these side groups and small bits and pieces in the structure of a polymer can actually influence the overall properties that we get. And we've looked at how these properties look in the macroscopic scale. We've looked at stress strain behavior and mechanical testing of polymers. We've looked at different classes of polymers and how they perform differently under different conditions. Be that temperature or other environmental conditions. This week, we're going to take all that into the design of a particular certain manufacturing process that could be most suitable for a particular polymer. So we're going to see how this comes all full circle and how we can use our knowledge of the structure and properties of polymers and their characteristics at different temperatures and different environmental conditions to actually find the perfect manufacturing process to shape them. And that is to be able to put them into a useful geometrical form. And also throughout this manufacturing process, you can actually also improve or enhance the properties of these polymers, similar to what we had in thermal processing and annealing last week. So the third week is going to be focused on different types of processes, manufacturing processes, to reshape polymers. We're going to look at how different polymers could be reshaped and deformed. Then look at additive manufacturing and how that certain class of advanced manufacturing processes has contributed to producing manufactured parts. And we're going to look at how we select a particular manufacturing process and what common types of manufactured polymer stock we have after the process is done. What sort of general geometries can we obtain? And of course, we're going to look at the end at some of the additives that are used in polymer manufacturing. We're going to look at some material that we add and mix into the polymer to improve its properties and also offer some certain useful aspects throughout the process. So we're still in chapter 15. The content here is part of this chapter, but there will be some references to chapter 14, as you will see. So in general, you know that polymers are divided to two main groups, thermoplastics and thermosets. And what's different is that, as we've mentioned multiple times, thermoplastics, as the name suggests, they're plastic at elevated temperatures, so you can actually heat them up and reshape, cool them down and maintain that shape. And examples of these are polyethylene, polypropylene, polystyrene. There are the materials that we previously explained. Thermosets, in contrast, cannot be changed in terms of their geometry when you heat them up. So when you form a network, it's rather permanent. So if you actually do want to reshape it, you have to then actually go to really, really high temperatures. They cross-link, they chemically form a network which is difficult to break. You can't melt them. You actually have to degrade that network. So in other words, they're not really useful in terms of recovering the material and recycling the parts. So if you actually cross-link it, similar to a lot of these materials that we mentioned, the epoxies and resins, similar to these light curable resins, you have to then actually, for instance, in nail cure, when you actually have an acrylic material, or when you have it in your teeth where you use light to cure the filler, there's no way to remove that just by heating it up. These materials are permanently cross-linked, so if you actually really want to destroy it, you have to dissolve it with a solvent. And so in other words, what you're doing is you're actually destroying it, degrading it. So really the materials that are useful for processing, especially at reasonably low temperatures, are going to be the thermoplastics. Okay, so what is a good temperature? You've already noticed that what we're going to use is temperature. So we're going to be using temperature to heat these stock materials up to a temperature where they can be deformed, and then we're going to use a manufacturing process to actually shape them. So what's the perfect temperature to process a particular type of polymer? So on the right hand side is a table that you guys are already familiar with. It's the glass transition versus melting temperature. So we discussed how these two are different. The glass transition represents a point at which the material crosses from sort of ductile material to a brittle material, meaning that it goes to sort of a glass state, and it could snap easily and break and crack to a very sharp and flat surface, basically crack, rather than in the case where it's a ductile material above the glass transition temperature, where if you stretch it or if you deform it, it's going to have a rather large elongation range until it actually breaks. And then we've got the melting temperature, which is the temperature at which the polymer goes from its solid state, which is in this case beyond the glass transition temperature, a rather ductile state, to a state where it's molten into a liquid, into gradually a viscoelastic material, and then a completely viscous fluid as you heat it further and further. Now, if you look at a couple of these common ones, so polypropylene, and the glass transition is negative. So actually at room temperature, it's got a ductile form. And the other ones here, a lot of them have a glass transition temperature that's rather high. So at room temperature, these are actually quite brittle. So if you find an object around you made of PVC, for instance, it's going to be quite brittle at room temperature. So you have to elevate it beyond 87 to be able to deform it. Whereas if you have an object made of PTFE or low density polyethylene, you're going to notice that at room temperature it's quite deformable. It's not going to snap when you exert some force on it. So all of these have this transition at different temperatures, but the melt temperature is always something positive. It's quite high also for a lot of these. If the glass transition is positive and it's quite high, then the melting temperature is also going to be a lot higher, as you can see here. So this is a sort of a unique case where PTFE has a glass transition that's negative, but also the melting temperature is quite high. In a lot of these cases, the melting temperature is quite high when the glass transition is also a positive value and quite high. So what you see here is that beyond this melt temperature, which is a few hundred degrees centigrade, you can actually observe a transition to a liquid. So what is the perfect place to do processing? If we choose somewhere in between here, you can deform it to some level, but not as freely as you want to. And when I say you want to, you'll see in the next couple of slides some of the most common manufacturing processes, how you actually need the material to be molten and liquid. Okay, so although you can deform it to some extent here, okay, but you typically want to go beyond the melt. Okay, beyond the melt temperature. So here you've got, for instance, polypropylene here. you have a melting temperature of 175C, and here the mold temperature. So there are two temperatures here. This is the processing temperature, in which case, in here we've got injection molding as our process, and we'll explain how injection molding works in a second. But let's say we've got a particular process here, but generally the temperature is common among different processes. They have differences, as I'll explain, but this temperature is where you want to be at for the material to easily deform and go into the shape that you want it to. So for polypropylene, you have 250, which is way above its 175 melting temperature. Similarly, for LDPE, low density polyethylene, you've got 160 to 260. It's also quite high, a lot higher than its melting temperature. For all of these, if you look, you'll notice that the temperatures are pretty high. They go well above their melting temperatures, okay? So what you see is we've got two different temperatures. For instance, for this particular process, and it'll be clearer when we get to injection molding, there's a processing temperature, which is a temperature at which you want to really have the polymer elevate to. And then you've got the mold temperature. You cool it down for it to go back to its stable state. So those are two different temperatures. So for instance, if you have polypropylene, you want to heat it up to 250 to 270 C. And then once you've injected it and you've made it into the shape you want to, you then cool it down to 50 to 75 C. And that will give you a stable manufactured object. So really the range we're looking for, depending on what your process is somewhere close to the melt temperature. You can go beyond that. We really want to try and go beyond that to get the best possible outcome. But in some cases, as you'll see, some special processes are okay with operating pretty close and narrow around that TM melt temperature. Okay, some processes you need to go a lot further, and we'll see why. And some processes are okay with a little bit less because they just want to give a shape to the material. They don't want to fully, as you'll see, fully melt it down and then inject it or whatever. They just want to forge a shape into your material. Okay. So the first process that we're going to look at is compression and transfer molding. Okay, so this process, as the name suggests, is that you have got a certain geometry that's designed into your cavity and mold design. So basically, you design a set of two pieces that contain a negative and positive geometry. This one that's extruded out is a positive. This one is actually a negative. And so when you use these two and you completely compress them together, so this distance is actually 0 here, there will be a region there that the material will occupy. And so basically it will take the shape that's going to be this minus that. So you're going to actually heat it up. Usually these bases and also the mold, both of these pieces are heated up. So you heat up the material until it's reached that temperature that you want to. Then you compress the extruded top piece onto the bottom piece, and that forces the material into the certain shape of the cavity. You cool it down and you remove the part. Now, all this will be a lot clearer when we actually do the next slide. And you can note here that it's not just thermoplastics, it's also thermosets. And this might confuse you a little bit. Well, I have to say, thermosets have two states, before they've been cross-linked and after. Here, it's before. So you haven't actually produced a material. You haven't produced an object out of this material. You've got the thermoset base material, which is a monomer. You put it here, and then you cross-link it into a polymer. Now that part that you've obtained there cannot be reversed. That's the point. So you can always take it from monomer to polymer, but once it's reached a polymer state, you can't reverse it. So what's interesting is that for thermosets, the polymerization actually happens here. Okay, so that's the unique part of it. If you've got a thermoplastic, you can also have it polymerized and then reverse it here into a different polymeric object. If it's a thermoset, this has to be a monomer where you put here, and then you actually put that monomer here, you cross-link it. Now it's permanently forever made into a polymer structure. And beyond that point, you cannot reuse it in this process. So that's the difference, okay? So this process, to get a better idea, works kind of like this. So you have these two pieces again, okay, the top and bottom plate, or some call this a plunger, and this is the extruded and basically the cut part, but it doesn't matter. There's two pieces to it, two parts of the mold. The reason I say it doesn't matter because it's not always as easy as two extruded and cut pieces. It can have internal pieces, it can have cores, it can have lots of intricate features to produce that part. So it's not as easy as just calling it an extruded part and a cut part. That's why you just call it the top and bottom piece of the mold, top and bottom plates. What's happening here is you put the stock in. That's the first thing you do. The initial polymer stock, what you're starting with. Now, if this was a material that was thermosetting, you would have a liquid here. But anyway, here in this case, you've got a solid stock. What you're doing is you're compressing it, and these two pieces are actually going to be heated up to the temperature that you desire. So the material is actually molten. Then what's going to happen is the part comes down, is going to squeeze those into the certain shape that you want, and the excess material is going to actually run all the way into these overflow grooves. And at the end, you're going to get the part with those extended region, and you need to actually cut those extended regions off to be able to extract the part. Okay, so a note that both of these plates, as I've mentioned, they're going to be heated up to an elevated temperature. And when you actually want to remove this, you want to open the top part and release it, you have to cool it down first. Make sure these have cooled down to a stable temperature. Then you remove the top part of the mold, and you can then eject the part. Okay, so again, note that if this was a thermoplastic, this could have been a solid block. If this was a thermoset, this has to be the monomer state. Okay, and then you have to actually cross-link it. So another note here is that conventionally these molds were kept at a certain temperature. Okay, so they were either heated or they were cold, and you would control this. The problem was that as you inject the polymer, the molten polymer mixture, into this cavity, what's going to happen is that because you've got sometimes really thin features, as it goes through this cavity, if this mold isn't at the proper temperature, it's going to cool down and solidify before it's reached all the points. So that's why you want to keep the mold at a heated temperature. Okay, so rather than having a single temperature, you want to start off by heating it up. So in the injection phase, it's actually heated and warm. And then you want to start cooling it down until it reaches the mold opening temperature, where now the part is stable and you can open the mold and release the part. Okay, so usually it's a temperature curve like that, and it can be a lot more complex than that. This is a basic, first level sort of improvement upon the very old and conventional processes where you actually have a control during the injection and cooling phases. Now it has gotten a lot more improved and enhanced from the state that it was here nowadays, and you can look at that in a lot of literature, both research and commercial injection molding research in commercial settings. Okay, so another process is injection molding. So what we had before was compression molding. Here we've got injection molding, and the difference is here you actually, what you do is you typically take the stock, you melt it down, you've got a spreader, so this is usually threaded, so as you use the ram to compress these beads or whatever solid stock you have in the feed, compress it into the threaded spreader, you also heat it up in this chamber. So you heat it up until it reaches liquid state, at which point it is injected from the nozzle into this certain cavity design that you have here. It fills up the cavity, and then you cool it down and you release this and move on to the next object. Another animation here to make that a little bit clearer. So you see the phases involved here. The first thing is you add the feedstock, you melt it down as it's going through this threaded spanner, and then it goes through the nozzle all the way into this region, which is, and then you actually cool it down and use those ejector pins to actually release the part. So these are the ejector pins. You need them to release the object. What you see here is the injection phase. Then we've got the object, you release it, and you move on to the next one. Okay, so the difference really is that here you're taking it to the liquid state, and then you've got sort of a syringe-like injection system, feeding it into the cavity, and then you're releasing it. Rather than in the previous case where it was a lot simpler, and what you had was you actually had the object there, be it a solid initial state or a molten initial state. What you do is you compress it into the certain shape. In this case, it's rubber. So this is exactly how they make car tires. Okay, into a certain shape, and then you're done. Okay, so it's a compression molding process versus injection molding, which, as the name suggests, you're injecting it into your cavity. Okay? So again, you should note that just like the compression molding process, where we had different operational different regions, here you also have a different temperature here in the feedstock throughout the extrusion process here in the threaded spreader region, and then all the way to the nozzle region where it's heated up and it's become more of a viscous molten polymer, and then a different temperature right here, which is pretty similar to the compression molding temperatures. It goes up and then down in the cooling phase. Another process is extrusion, and it's very similar to injection molding. The only difference here is that you still have the process of taking it from the feedstock all the way to the manufactured stock here, using this sort of a threaded sort of screw that you've got, similar to what we had before in injection molding. And this barrel is always heated, again, similar to the injection molding process. And then the molten plastic, it's going to be heated up through this shaping die. Okay, so this isn't, this is no longer a nozzle that injects it into a certain cavity design. It's going to be a shaping die. And what it does is that it has a geometry in this certain opening here that dictates what you're extruding out there. And this is a continuous process. So as this goes through the shaping die, it's going to cool down and the shape is going to be finalized into it. So as you can see here, this is the idea. You're actually extruding continuously these long 2.5 dimensional extruded objects that just have the same cross section throughout, but a super long and extruded. Okay, so this can have many different geometries in terms of its cross section based on what the shaping die looks like. Okay, so that's how you get these long extrusion bars and stuff. So it can be used for a lot of different applications, as well as you can just extrude, you know, films and sheets. You can extrude tubes, as you can see here, or it could be a lot more complex designs of like what you've got here. You've probably seen these in household items and commercially used products. So that's the third process. The next process, which we're going to introduce, is blown film extrusion. Again, from the same class of extrusion processes, similar to injection molding. Again, it has a heated barrel, and the extrudate goes through another piece. In this case, the special piece is actually pretty intricate. It goes through sort of this nozzle here, then it comes into this tubing die. And so it fills in this part, and then there's an opening here, a channel, where you're injecting air at a high pressure. And then what happens here is that as you inject the air, what's going to happen is that this opening here is going to expand. So the plastic, the molten plastic, is going to go around, and then the air here is going to produce a really huge bubble. And that huge bubble here is going to form something similar to a balloon, basically. And so when you run that, you know, really thin layer of polymer, which in this case is going to be like a bag, through these sets of rollers, they're going to flatten it out. And depending on how much you compress it and at what temperature, it could collapse the cavity and form a sheet, or it could maintain the cavity and make a bag. Okay, so the idea is you blow into the plastic, you form a really thin sort of layer, and then depending on these rollers, what temperature they have and at which point they're doing it and how much they compress it, they can either form a sheet of film or an open bag. Okay, so that's exactly how they make a lot of the consumer grade thin film sort of objects. So that's some of the most common polymer processing methods. And what we're going to do after this is we're going to look at 3D printing technologies. But before we get there, I'm going to give you a break. That's going to be the topic for the next lecture this week. What we've covered so far was some of the conventional manufacturing processes that have been used for many, many years. Beyond this point, we're going to look at the advent of these new processes called 3D printing processes that belong to a class of additive manufacturing processes. And we're going to look at how they can add to the capabilities that we already have. Note that these processes that we've covered so far are in some sense not additive. You have the same volume of material maintained throughout. Now we'll see why additive processes are called additive in the next lecture. But before we start the next lecture, I'm going to explain the difference between additive, subtractive, and zero processing. And you'll see how a lot of these processes are zero processes in terms of the classifications that I just mentioned. So we'll continue the chat on manufacturing processes in the next lecture. And for now, we'll leave it there. Okay, take care.